From the set of numbers, square root 25, 17, 121, and the square root of 32, write down a perfect square. Now, what is a perfect square? Well, a perfect square is a number that can be expressed as the product of an integer multiplied by itself. For example, 121 is a perfect square because 11 squared is equal to 11 times 11, which equals to 121. So perfect squares, examples of perfect squares would be 1. 1 is a perfect square because 1 times 1 is 1. 4 is also a perfect square because 2 times 2 is 4, right? And then we have 9. 9 is a perfect square because 3 times 3 is 9. Then we have 16. 16 is a perfect square because 4 times 4 is 16. Then we have 5. 5 is a perfect square because 5 times 5, then we have 25. 25 is a perfect square because 5 times 5 is 25. And then we have 36. 36 is a perfect square because 6 times 6 is 36. And so a perfect square is a number that can be expressed as a product of an integer multiplied by itself. All right. And so in this particular question, 121 from the set of numbers, 121 is a perfect square because 11 times 11 is 121. And that's our answer for this particular one. Let's move on to part B. It says, which one, they want us to write down an irrational number. What are irrational numbers? Well, irrational numbers are real numbers that cannot be expressed as a simple fraction ratio of two numbers, and their decimal representations are non-terminating and non-repeating. So first things first, irrational numbers, they are not fractions, right? So irrational numbers are not fractions. So if you have a fraction, then it's not irrational. More specifically, if you have a fraction of two integers, right? So irrational numbers are not simple fractions of two integers, right? That's more specific. So if you have a fraction of two integers, then it's not irrational, all right? Because you cannot write an irrational number as a fraction of two integers, right? That's said more specifically, right? Okay, what else do we know about irrational numbers? Well, their decimal representations are non-terminating, which means that irrational numbers can be expressed as decimals. But when we look at their decimal representations, number one, it's non-terminating, which means that it goes on forever and ever. And number two, it's non-repeating, which means that it doesn't follow a consistent pattern. So let's look at these numbers. So this one is the square root of 5, and the square root of 5, this one is the square root of 25, and the square root of 25 is definitely 5, right? That's the square root of 25. The square root of 25 is definitely 5. But what is 5, right? 5 is equal to 5 over 1, right? And so that means that the square root of 25 can be written as a what? As a fraction of two integers, which means that it's not an irrational number. Then we have 17, right? 17 is a prime number, and 17 can be written as 17 over 1. It can be written as a fraction of two integers, right? And so 17 is an integer, 1 is an integer. So that means that since 17 can be expressed as a fraction of two integers, it's not irrational because irrational numbers cannot be expressed as a fraction of two integers, right? Then we have 121, right? The same is true with 121. 121 can be expressed as 121, right, over 1, right? So it can be expressed as a fraction of two integers. So that means that it's not irrational because irrational numbers cannot be expressed as a simple fraction of two integers, right? Now let's look at the square root of 32. Well, the square root of 32, if we express that as a decimal, right, it's equal to 5.6568542449, and the list goes on. So the square root of 32 is a decimal that does not end and that doesn't have a consistent repeating pattern. So that means that the irrational number from the set of numbers is definitely the square root of 32. And that's our answer to this question.